students. I hope you're getting ready for your midterm and I wish you the best. So here I go through a quick revision of what the key factors, the key elements that we have studied for the material of midterm 2, which starts at chapter 3, the data link layer, DLC, and continues through chapter 4, the networking layer, and then chapter 5, queuing theory. Okay, so in the data link layer, we studied the framing, so how to label the start and the end of a frame. And in that part, the main focus was on two important approaches. The first approach is using a length field. So the start of the frame is labeled, and then you don't really label its end, but you give a particular field that comes immediately after the label, which tells you how long is the frame. A key parameter to calculate in this case is how long that that field should be, and it depends on the maximum size of the frame of the packet. So if the maximum size of the frame of the packet is, for example, 1000, then you take the log to the base 2 of that number, and then you approximate it to the higher integer. That's why we add 1 here. It's not necessarily going to be adding 1. So for example, if it was 1024 and you take the log of that is going to give you the exact length. But if it comes with a little bit of a fraction, then you round it up all the time. Okay, so that's the idea here. So that's the first thing, which is the length approach. Approach is to mark the start and the end using the bit-oriented framing. And there was one important thing here, which is how to avoid the appearance of the same marker for the start or the end, the flag. How do you prevent that from happening in the middle of your frame? Because that will indicate to the receiver in a wrong way that the frame has finished, right? And the idea here was something called bit stuffing. So if your frame had the frame indicator or the flag had k bits, k ones, right? You care about the ones, so k consecutive ones. Then you need, whenever you encounter k minus 1 consecutive ones, to insert a 0. That's called bit stuffing. And then at the receiver, we have been through the algorithm how to remove the stuffing. So whenever you have k minus 1 followed by a 0, you remove that 0. If you don't have a k minus 1 followed by a 0, k minus 1 ones followed by 0, you don't remove it. And then you get your data back. And then what we needed to calculate in this case was how much is the overhead. So how much, so we have in any frame, we have our data. That's a general concept, by the way. So we have our data and then other stuff, things like the error correction, added bits, or things like the flag and so on. So the efficiency of our system relies on the ratio between these added bits for whatever, for addressing, for error control, for framing and flagging the start and the end, the length field. All of these are not that these are bits that are not carrying information, so they are an overhead. So we always need to figure out how big is that overhead versus how big is the part carrying information, and then we can calculate the efficiency accordingly, and the efficiency is going to be the overhead divided by the total length of the packet. So again, as a quick reminder, if this is your packet and your packet contains information in this part, and then the other part, for example, has the flag, it has some error control as well, it has maybe some address, and maybe some other information here. So the length of this, okay, is what we call the overhead, right? And this part, the other one, is the information bits, right? And then, so let's call this I, and the overall length of the packet containing both of them is L. So the overhead is the total number of bits contained here. The information or the useful information side is the total number of bits here. And the L is the total number of bits in the whole frame or the whole packet from start to end, including everything, right? The efficiency in this case is going to be the information part, right? Information divided by the L, the total L, which can be written as information divided by information plus overhead, right? So this is how we can calculate the efficiency. And I remind you, whenever we are doing the efficiency, it's not necessarily just one overhead here. There might be many of those overheads. As I mentioned here, it can be the flagging. In addition to that, we might have some error control part, the added bits for error control, like what we do in the next part when we discuss error control. It can be address. So I put the source address, destination address, some other things, and then the part that carries the actual information that needs to be transmitted, okay? So you might get a question which not only includes a flag, but a flag and some other stuff, and all of them are overheads. So be careful when you are calculating the efficiency, okay? So over here, it's just focused on the overhead related to flagging. And for this particular case, with the bit stuffing and everything, the expected value of the overhead has this expression, where L is the length of the packet. So that's the total length of the packet. And K is the number of ones in the flag. So that's the flag length, the number of consecutive ones in the flag itself. And then we have the calculation of the total overhead given by this formula. And then there is another formula that tells us for a particular system what is the optimal value of K, the flag, the number of consecutive ones in the flag. And that is given approximately by this, which is just a result of solving the derivative equals to zero, famous formula for getting optimality. And this is optimal in terms of giving the highest possible efficiency, right? We looked at error detection, and then we looked at two methods of error detection. The parity, which adds extra bits to the system based on calculations done from the actual information bits. And we looked at the CRC, which does the same, but the way of calculation is rather than being just linear binary equations, they become nonlinear equations that uses some division methods, as we'll see later. Before going into the two different methods, we looked at what are the parameters that we use to calculate the efficiency of any error detection method. We looked at something called the minimum distance. So you have to know what's the minimum, how to figure out the minimum distance between any two binary strings, binary like array of bits. And then we also looked at something called the burst detection capability. A burst is a set of bits consecutive to each other where an error happens. Again, we mentioned that in the lecture, so you have to be a bit aware of what's happening there. And then also we looked at something called the probability of random bit error, which is typically given by this expression that we see here, right? So these are the different parameters that we can use to figure out how good is an method. Parity check method, so you have K data bits, you have R check bits. Your code efficiency is K divided by K plus R, right? So that's actually the overall packet. And then this is the information part. This is an overhead part. As we said, overhead can be of many types, right? So those R's are overhead, right? Something called the coding rate, which is basically R divided by K, right? So that's called the coding rate. And as a reminder, so when you see the word, you remember what does it mean. So anyways, these are general for any coding method, not just for the parity check codes. So they also apply for the CRC. So the parity check, the general idea here is that it's calculated by each one of those bits, and the parity check bits is calculated as a linear formula from the other bits. There is a special case from that, which is single parity. Single parity is either even or odd, as we discussed in the lecture. And for For that one, you can calculate the probability of undetected error using this formula. We have before, and then the other type is the cyclic redundancy check. So for the cyclic redundancy check, the difference is that, again, those parity checks are calculated in a different way. I'm not going to go through what does this mean. We have described that in the lecture already. And general idea is that the way that this is implemented is using shift registers. So how to implement that in a real system. And remember how you can calculate the R bits if you know the data bits. So if you know the K, the message itself, which is composed of K bits, how can you calculate the parity? Using the long binary modulo 2 division. We have done a couple of examples. You had that also in your assignment. So you should be. And also, if you want to check for the error, you repeat that operation. So you receive the full message, including both the message and, the full packet, including both the message and the CRC R bits, right? And then you take that and you divide it again by the generator matrix. And there is no remainder, then there is no error. And if the remainder is not equal to 0, then there is an error, right? So this is how you perform the error detection on both methods. Last thing is a reminder that generally speaking, when you talk about physical layer, we are dealing with bit error rates, the probability of a single bit having an error. Now, when we deal with data link layer, we deal with packets. So what we really care about is the packet error rate. And we had a formula that allows us to calculate the packet error rate from the bit error rate. And we described clearly with a lot of explanation in the lecture why the formula has this. But anyways, if you are given a particular bit error rate and a packet of a certain length, you can calculate the packet error rate using. Okay. Now, after doing error detection, if I want to do correction for errors, so I want to recover from a message that was arrived in error, the only way to do that in the data link layer is using automatic repeat request. So I ask for the message to be resent again to me if I detected there's an error in the message, right? And there were 3 methods: stop and wait, go back N, and selective repeat. Well, we looked at the time sequence diagrams for those ones as a description of the method. We also have solved some problems that incorporates putting a detailed time sequence diagram. So to relieve you, I'm not going to ask you to do, I mentioned that already in the announcement, I'm not going to ask you to do those specific scenario time sequence diagram for the ARQ. So you don't need to spend a lot of time there because I've seen that many of you gets confused throughout the process. So I'm not going to get that into your exam. Stop and wait, you don't send the next one until you get the acknowledgement. You get the acknowledgement, you send the next one. Otherwise, you keep waiting. There is a timeout so that you cannot wait forever. After that timeout, you assume that either the acknowledgement was not received or your packet that you transmitted was not received, so you retransmit the packet again. If you get negative acknowledgement, which means that the receiver figured out an error, you retransmit the packet. Now, in addition to describing the methodology, we also looked at how you can calculate the efficiency of that system. And there is always efficiency with error and efficiency without error, right? So we have done, you should be able to calculate both of these for this method, the stop and wait. Now we go for another method, which is a little bit more efficient in certain cases, which is called the go back N. In that case, you have a window of a certain number of packets. You keep sending, you don't wait for acknowledgement of individual packets. But if you reach the end of the window without receiving any acknowledgement, then you stop at that point, and then after a certain timeout, you will retransmit whatever is inside the window. Now, if while transmitting the packets inside the window, you start getting acknowledgements, the window is shifted. Key important thing, the window is always shifted when the first packet in the window has its acknowledged receipt. Okay, then the window will shift. Okay, so the window will keep shifting, right? And at any point in time, if you receive a negative acknowledgement, everything in the window is going to be retransmitted, and then the transmission will continue from there. That's the idea of the go back N. Again, for that particular method, we looked at the efficiency, and again, efficiency without error and efficiency with error, as we see it here. Should be able to calculate those and should be able to understand all those parameters that you see there and the different conditions for this situation, right? So how N is determined, what's the minimum possible value for N, what's the timeout, right? So you have to be really able to figure out these parameters as you see them here. And we have solved a few examples. We have also had some assignment. Selective repeat is very similar to go back N with only one difference, that whenever a negative acknowledgement or a timeout happens, we don't resend everything in the window. We only send the specific packet within the window that we got a negative acknowledgement for, or that we got no acknowledgement at all due to timeout. Okay, so that's the difference between selective repeat. And selective repeat, again, is more efficient. It's a little bit more complicated, requires reordering at the receiver side because you might receive packets out of order. And the efficiency for selective repeat, generally speaking, if no error happens, right, so you keep transmitting, so you will never waste a single minute or a single element of time, so the efficiency is equal to 1. Now, what if an error happens? If an error happens, the calculation shows that the efficiency is equal to 1 minus capital P. What's capital P? Is the probability of packet error, okay? And that appeared also in the go back N, by the way, that capital P. Okay, so keep in mind that in the case of go back N and the case of selective repeat, you will be needed to calculate packet error rate if not given to you. If, for example, you are given the bit error rate, then you need to calculate the packet error rate from that so that you can use it into the formula. And also we have been through this in your exercises and in your assignment. Okay, so next thing, the last part of the data link layer, which was the largest part actually of this module of the course, the one after midterm 1 until midterm 2, we looked at the medium access control. So in the case that the medium of communication between one point and the other in the network is shared between many nodes. So it's not really specific only to a single node link. So it's shared, for example, a broadcast in the wireless, or the case of a bus where everyone is connected to that. We need some way to coordinate who talks and who listens, right? And within that, we have looked at specifically a certain type, which is the contention-based approach. And within the contention-based, we focused on random access. And actually, even within random access, we are more confined to only the Aloha and the carrier sense multiple access techniques. So these are more common in our nowadays technology. Most of the other ones that you see here are no longer in use. And at the same time, they are quite historic. So they have a simple representation when they started, like the Aloha, and then the carrier sense in its simplest form, but they kept evolving with us until they are used in nowadays Ethernet and nowadays Wi-Fi, right? So those are very important. They represent the idea, and at the same time, they are current technologies until the days that we're right now. So we started with the Aloha. Aloha, simple method. Whenever you have a packet, just transmit. So not just the easiest way to do transmission. And because of that, collisions can happen. So more than one can transmit at the same time. This will cause a collision. In the case of collision, a retransmission will happen, but with different random waiting time to avoid repeated retransmissions, recollisions. So to minimize the probability of that happening. Again, we not only looked at the method itself, the Aloha, but also we looked at how we can calculate its throughput. And throughput is the amount of data successfully transmitted per unit time. And we got this expression for the throughput. So you should be able to calculate the throughput of an Aloha. And this is the maximum. It's a fixed number, the maximum for a pure Aloha that can be reached. But we are shown how you can get this maximum again by doing a simple derivation equating with 0. So you should be able to actually calculate the performance or the throughput of pure Aloha. So we looked at the case where time is slotted, so the slotted Aloha and the performance is slightly better, and again, should be able to calculate the throughput. We moved from the Aloha to a smarter one, which is the carrier sense multiple access, where you just don't really transmit directly, but the node will listen first to make sure that nobody is transmitting, and then it will start the transmission. Again, in that case, a collision might still happen, right, as we see here. And there were many methodologies of doing that carrier sense multiple access technique. So we looked at all of them. So we have, again, for the non-persistent case, which means that you don't really transmit immediately, but you wait a little bit before transmission. There is an unslotted and slotted version, and also for the persistent, there is one persistent and P-persistent, and again, slotted and unslotted for each one of them, right? So all the variations are. Particularly, we looked at the non-persistent case, described the protocol, and was able to calculate its throughput again, and both for the non-slotted and the slotted case, to calculate that directly from the formula. Similarly, we have done for the one persistent, so we've described how the method works, right? And then we looked at the throughput formula, both unslotted and slotted. Then when we went for the P-persistent, we only mentioned here after describing it, we only mentioned that it is a trade-off, but we didn't really have formulas for the calculations of the throughput. It's a bit complicated, so that's why it's not done here. But anyways, in all these formulas that we have seen before, because I noticed that some of you gets confused. So the small g, which is given in those formulas, is what's called the offered load, not the normalized, but the offered load. And that is simply the packet arrival rate. That's the number of packets arriving per second, the average number of packets arriving per second, right? Sometimes you need to calculate everything in bits per second. So if you have it in packets per second, you just need to multiply it by the packet length to get it in bits per second, okay? The other thing is, if you know the non-normalized, like the one which is calculated packets per second or bits per second, and you want to get the capital G, the normalized version, it's simply that non-normalized version multiplied by the time duration t, and that time duration t, the normalization time, is actually the packet transmission time, which is called the packet transmission delay. If we are dealing with a slotted system, the slotted system is already designed such that the time slot itself is equal to the packet transmission time. So it will be the same. Whether you say it's the packet, the time slot, or it's the packet transmission time, they are equal to each other when we are dealing with a slotted system. When an unslotted system, there is no such thing as a time slot, and our capital T is actually the packet transmission delay. What is the packet transmission delay? As a reminder, simply it's the packet length divided by the transmission rate. So if I say that the system is transmitted at 10 megabits per second and I have 1 mega bits packet, then the packet transmission delay is equal to the 1 mega bits, right? The length of the packet divided by the transmission rate in bits per second on the medium, right? So, okay, now I told you how to calculate all of these. We have solved problems on that. We have got, I don't remember whether it was for section 51 or section 01, but we've got also the a question in the quiz which required you to do this calculation. So anyways, it's in your assignment, so you should be able to do it, okay? That is for different access technique. One important note for all of you, you should be able, given a curve like this, which describes the performance of different methods. And by the way, I can give you the curve for methods that we have not studied here, but you just see the different curves. You should be able to do two things from these curves. Given a particular traffic load, normalized traffic load, right? You should be able to calculate the corresponding throughput. So, for example, if I give you a traffic load of a normalized traffic load of 4, and I ask you to calculate the throughput for non-persistent sigma, so you will take that here. Here is the curve for the non-persistent, and here's the corresponding throughput, and you can get it from the figure. Right? So that's one thing. And then again, because this is the case for each one of those, right? If I ask you at a particular load, which of these methods has you would select as a designer, right? So for example, if I want to compare the non-persistent sigma with the 0.5 persistent sigma, right? So this one, right? So if I'm a designer and I have an offered load to my system, which is 4, right? A normalized offered load, right? Will I choose this guy, the 0.5, or will I choose this guy, the non-persistent sigma? Clearly, the throughput here for this guy is lower than the throughput here. And I always need for my system to have a better throughput, right? So I will select this one definitely, not this one, because the throughput here is higher than the throughput here, right? And you have to give numbers and then justify why you selected this or that. So you should be able to deal with these performance evaluation curves if given to you, even for protocols or medium access control methods that you have not studied. They are just curves They have the traffic load versus the throughput, and just from the curves, you can answer either numeric questions or comparative questions as I did. Okay. We have also looked at the more advanced version, which is the carrier sense multiple access with collision detection. We've described how it works, right? What's a collision detection, how it makes the system more efficient. And then we have seen some of the curves for the different parameters alpha. Okay. Again, you have to be aware what's alpha, right? It's mentioned there in the slides. So you should be able to know what is this parameter. And again, given curves, you can solve things. We did not have a formula for the carrier sense multiple access collision detection. There is one, but it's a bit complicated, so we didn't have it in our study. We looked also at the modified version for wireless. So the carrier sense multiple access collision detection works for the wired, which is called the Ethernet nowadays that we use. There is the carrier sense multiple access collision avoidance, which works for the wireless. In wireless, collision detection is almost impossible because you cannot measure the energy at another node, so you will never know that a collision happened. However, collision avoidance is performed, which is trying to avoid the collision ahead of time by introducing the random waiting back off and those DIFS, SRFS, and so on. So we gave a collective description for this, but we didn't any formulas. Now we moved after that to the network layer. Few things are key to what we studied in the network layer. Number one, that routing in a communication network can have two types, fixed and dynamic routing, and you should handle a routing table with fixed or as we see in those slides and figure out where are the routes from one node to the other, looking at those tables and what do the two different tables do. Why do I have multiple routes in the dynamic case and a single route only in the static? And then we looked at probability of blocking calculations using what's called the Lie graph. And particularly, we have studied how to calculate blocking probability for series connection, parallel connection, and then we had an example of many series and parallel connection combined together, right? So you should be able to do that for any given graph. One important note here is whenever I give you a graph and I ask you for calculating the probability of blocking from one point to another point at the end of the start, at the end of the graph, you always assume that the different routes that you will go through are independent from each other, even if they have some links common between them, because practically those common links will make them not independent, but we always assume that they are independent, okay? Because that simplifies the calculation. So you'll calculate, you will look at the different paths, right, from start to the end, and you assume that they are independent from each other, and then you start calculating the routing the blocking problem. Okay. We also looked at routing strategies or routing techniques, and we had the two that are depending on the topology, the fixed and the adaptive. Adaptive is the mostly used one. However, fixed can be useful in very, very small networks, which are not dynamic, do not change that much. We also looked at two methods that do not rely on the topology itself, so you don't need to know how the network looks like. This is flooding and random routing. And the idea here is that those are still important because they are used in the situations where you are still exploring the network. So you don't know yet, you are still configuring the network, for example, or the network has changed significantly due to drastic upgrade or downgrade or drastic breakdown or whatever. Then in that case, those methods will ensure that you can still communicate even though that you are not aware of the topology sufficiently, right? So the flooding and that are still important. We looked also at another method other than the Dijkstra algorithm, which allows you to figure the shortest path, and it's called the Bellman-Ford. It's just based on exploring the path from one node to another node using successive calculations. So you start with figuring out the cost for all single link paths from that node to other node, and then double link, and then triple link, and so on. And each time you keep the one with the shortest distance until you finish exploring the whole network, and then you have the shortest path from a source to we moved after that to the queuing system. So first thing, we showed how to represent the queuing system and what are the different elements, right? and what can be modeled using a queuing system. We give many examples about that. Typically, you are giving arrival rate and departure rate from the system, and you are asked or departure service time from the system, and then you are asked to find the waiting time and the length of the queue. In that case, we use something called lattice formula. One important note in lattice formula is that when we talk about T, we said that it is 1 over mu, right? And we have used mu in two different contexts, and maybe you had a confusion assuming that they are the same. So when we were talking about lattice formula, mu was actually the average service or the average exit rate from the system. So if you are waiting outside the bank, you are not really looking at the teller and seeing how long it takes the teller on the average to service one person. But no, you're just waiting outside the bank, and then you are calculating how many customers are exiting the bank, and then averaging that, and then converting that into an average service time. That's an average actually overall time spent in the system. So that mu was not the mu that we used later on when we were doing the queuing analysis as the server capability rate, right? So keep that in mind. That's why we're saying take 1 over mu. That will give you the waiting time inside the system. It's not just the waiting at the server, it's the waiting inside the whole system, the queue and the server, okay? And then you can use that into lattice formula, which says that the number of packets inside the whole system is equal to the arrival rate multiplied by the waiting time inside the whole system. Okay. Later on, we looked at the more detailed analysis, and particularly we focused on the MM1 queue, Markovian arrival, Markovian departure, single server, and of course the fourth parameter, which is K, the buffer length. If it's omitted, if it's not mentioned, then this means that our memory here is infinite, so we will never run out of memory. Okay. There are these important assumptions that you have to keep in mind in order for us. We have done the analysis using the Markov chain, so you should be able to kind of list the steps of the Markov chain and perform the analysis as needed. Understand what's the probability of the different states. So, for example, if I tell you that and I mentioned that example in the lecture. So, if I tell you that we have a particular indicator that says that a particular award is being given whenever we have the queue length equal to 10. So this means that we are interested in state k equals 10. And then I ask you what is the probability of having that? Then simply this is the probability of being at state 10. It's not really anything else, which means the probability that the queue length is equal to 10. Should be able to interpret those things that we did here and understand how they look like. And also you should be able to use the final formulas that allows you to calculate the average length or the average number of packets inside the whole system, the average waiting time inside the whole system, the average waiting in the queue only, the number of packets inside the queue only, excluding the server, and so on, right? And we had a few examples, a few problems on this and on lattice formula in the assignment. And also, by the way, while doing this analysis, we had to use lattice formula a few times, right? So the analysis is detailed in your lecture. And that was the last thing that we did. I wish you the best. Please focus. Your exam is gonna come in terms of length, very similar to the previous one. So it's gonna be the same number of questions approximately. It's gonna span this amount of information that I've talked about right now. The key things that I stressed here, you need to keep them in mind and understand how they are done. And if you have any question, you should figure out that or resolve that before your exam. You can email me from today until tomorrow's morning. After tomorrow morning, 8 a.m., I'm not going to be able to respond to any emails. Your exam is going to start tomorrow at 11:30 and it's going to finish at 1. So it's from 11:30 to 1. Particularly, actually, it's from 11:30 until 12:45, which is 1 hour, 15 minutes, the exact lecture duration. And it's going to be in your classroom, the same classroom used for your teaching. That applies for both the male and the female students. So you go to your classroom before 11:30. We'll start immediately on 11:30. This time is selected so that it doesn't interfere with the rehearsals happening in the morning and the rehearsals happening in the afternoon, and those who are taking some of their courses or stuff. So basically, this way, I hope we will serve everyone, and good luck in your exam tomorrow, inshallah. I'm gonna send an announcement about that also. Okay. So again, I was saying, in addition to listening carefully to all the important notes mentioned in this review, you need also to be aware of what happened in your assignments that you had, because the questions are gonna be like spanning the ideas that you had in your assignment, in addition to whatever I mentioned here as a key important thing to keep in mind. Good luck to you, and see you in the exam day, inshallah. Assalamu alaikum.